let's get started. So I'm very delighted to introduce you the keynote speaker for these sessions. Is Gavin Ananda, that is currently the lead for the perception team at Zipline. Together with this team is developing systems that allow to perceive and reason about environment in real time and to make better decision making for their own vehicles. Now, if you never saw Zipline, if you know what is a Zipline, you are up to a good treat. Zipline is, to me and to many, is one of the best examples of how robotics can really change and revolutionize, actually, and get an impact for social good. Zipline has a fleet of autonomous aerial vehicles that they get deployed under different conditions, different weather, day, night, and they can autonomously reach area, for example, in Ghana, in Rwanda, and even the United States to deploy goods and even medical supplies. So that's fantastic. Again, they're pretty much fully autonomous. They have like minimal intervention from the humans. Today, Gavin is going to give a talk about their tactical detect and avoid systems. We're going to also provide some details about their novel sensor architectures that allow to deal even better with different type of weather conditions, even deal with other type of vehicles to share the airspace. So without further ado, please let's welcome Gavin, and we are looking forward to his talk. Thank you.
Thank you so much. Can you hear me? Is this better? Check 1, 2. Can you hear me? Louder? All right, we might need to bump that up a bit more. Okay. Can you hear me now? Check. Check 1, 2.
Yes.
Check 1, 2. Check 1, 2. Check 1, 2. Check 1, 2. Cool. It tripped it. We'll wait for a few minutes and get started. No worries. As long as something turns on.
No, it's the speakers in the room. For some reason, they shorted out, so he's going to check the amps in the back room, and then we'll get started. Check 1, 2, 1, 2. Check 1, 2. Hey. 1, 2, 2.
I can shout. Yeah. I can shout. I'll try to be as loud as I can.
It shouldn't screech. Yeah, somebody's working on it. Well, okay. Great. End of the hallway. Check, 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 check.
But can folks, other folks hear the...
Yeah. Yeah. It's just the house patch. He's trying to mess with some stuff now, change the input and stuff like that. If you guys want to start, okay. You're gonna have to talk real loud. I can close the doors. Try to cancel out some noise.
Okay, so there are some issues with the speakers we're trying to resolve. So what we're going to be doing is that either you guys can come a little bit closer, that would be nicer. We're going to try to make Gavin scream a little bit, but we're going to start.
A bit louder.
Okay, so hopefully you can hear it, but we're going to start, and then hopefully we're going to solve the microphone issues shortly, okay?
Yep.
Okay, let's thanks again, Gavin. Okay, welcome.
righty. I'm going to check. Top left corner. Can you hear me? Top right. Can you hear me? All right. Perfect. Let's get started. So my name is Gavin Ananda. I've been at Zipline for approximately 4 years, and I lead the perception programs at Zipline. Today, we'll be focused on one of these programs, Detect and Avoid. I want to take you on a journey of developing a novel detect and avoid system from start to production. This is a brand new technology, and I'm really excited that you're going to be the first to hear about this technology outside of Zipline and the FAA. But first, I want to give you a quick primer of Zipline's mission and our current scale. One second. All right. Our core mission is to provide every human on Earth with instant access to vital medical supplies. It has guided our company from its inception and has been our North Star in all the decisions we've made. Our means of achieving this is via a fixed-wing drone that you see on the right that we call a Zip. And it delivers the supplies via a parachute drop box, as you can see on the bottom left, on the bottom right. This is done at a hospital or a healthcare facility. We started initial operations in Rwanda more than 5 years ago, and now have reached a national scale of 24/7 operations where we serve 90% of the populations for all types of medical deliveries, 250 plus products in total. This is done via 2 distribution centers that we call nests. The distribution centers have a service radius of about 80 kilometers that you can see in the circles at the bottom there. Similarly, we've been operating at a national scale in Ghana, where we have a total of 6 distribution centers and 2 more under construction. More recently, we started operations in Japan, US, primarily in North Carolina and Arkansas. Our US ops are actually low volume as we are going through certification at the moment. We also plan to extend our footprint this year to Nigeria, Cote d'Ivoire, Kenya, and Utah. So how does our system actually work? An order is initially placed by a healthcare provider. This can be done via our fulfillment system or WhatsApp message. Once our fulfillment operators receive the order, they pick and pack the product in a cardboard package and put it in the Zip. The assigned Zip is then launched from our distribution facility, where it travels autonomously along a pre-planned route to the target destination. This is done at approximately 300 to 400 feet above ground. As it reaches the destination, the Zip then informs the customer of a pending arrival and descends down to a lower altitude of approximately 100 feet. And parachute drops the package to an assigned target destination. We typically achieve a 6-meter radius accuracy, about 2 parking spots. Once the order is delivered, the Zip returns back along the same route to be recharged and reloaded for the next order. So here's a little video that gives you a sense of what the operations are in Rwanda. What you see is a typical flow from our fulfillment operators that have packed and assigned the product to the facility. The flight operator receives the package and assigns the package to a Zip prior to loading it to the Zip. As you can see, the package has a paper parachute that's clipped into the payload bay of the Zip body. What you notice is the vehicle is divided into 3 main components: our body, our wing, and the battery that is designed to be interchangeable. These, in addition to our foam nose cone, is assembled on our launcher prior to every launch. So as an aside, the launcher that we use is a catapult launch system that accelerates our vehicle from 0 to 110 kilometers an hour in 0.3 seconds. This is done to handle the wide range of wind conditions that we have to operate in. Once assembled, a series of pre-flight checks are performed by our flight operators, as you can see. This ensures that the vehicle is in nominal conditions. In addition, internally, there's over 450 plus software pre-flight checks that are performed prior to enabling the launch of the vehicle. All of this is done within a minute of when the battery goes into the body. This is to ensure we can hit the flight volumes of more than 200 flights a day within a 12-hour span. Now, it's already been about a minute since we have the battery has been placed, and the Zip is about to be launched right now. And so once it launches, it just heads to the facility. The impact of our service has actually been immensely felt in our facilities in the facilities that we serve. Independently published data has shown that Zipline facilities are 42% less likely to reject a patient seeking a vaccine due to stockout, and vaccine stockouts are 60% shorter in Zipline served facilities. This is extremely meaningful in that it directly impacts the vaccination rates of a population. Zipline served facilities also stock 10% more products. The availability of more products directly translates to better healthcare outcomes for the population. Blood is a scarce resource around the world. A lot more blood than you would think expires on the shelf before it can be used. By centralizing the blood supply and delivering it on demand, we have reduced blood wastage by 2/3. This means many patients that were not getting blood that they needed are now getting that blood. Shown here is a typical morning at a Zipline facility in Ghana. On the top right is actually a fulfillment area. On the bottom right is actually a launch and recovery area. Our recovery system is designed to recover vehicles similar to an aircraft carrier. There's a little A-frame structure you see there. I'm not going to go into too much detail, but I encourage you to check out videos on our website. On the left is actually a visualization of what the controller of our Zips watches on the iPad UI. The red nodes are 300 to 500 healthcare facilities that are served by our distribution center. Zips en route are shown in white arrows, and zips returning back are in black. At any one time, we can have 20 zips flying along the same route in the air. At the moment, we can fly up to 28 zips at any one time, delivering to our customers. Here, it's easy to see that these facilities are dynamic environments that have unpredictable demands and emergency orders that make it difficult to schedule everything that we need. Just within a 4 to 5 hour span, we have done 71 package deliveries of about 550 products. To give you a sense of the scale of all our flight operations, here was a busy day last week. In total, from our facilities, we have had 855 deliveries, where a maximum of 124 zips were flying simultaneously, with an average flight distance of 125 kilometers. This translated to a total flight distance of 107,300 kilometers flown, which is equivalent to 2.6 times around the equator of the Earth in one day. So as we discussed, the level of scale to be able to achieve 28 zips at once in a shared airspace requires shared airspace and shared resources. We think of this as airspace autonomy. It is really difficult to predict when a zip will be and when it will need to modify its mission. As a result, there needs to be an online algorithm that keeps our zips safe. Our zips are at times in places where there's no cell or connection, and there's literally no phoning home. So centralized planning algorithms actually don't work. So what we've designed is a distributed collision avoidance algorithm and distributed resource allocation algorithm. There's only one launcher and one recovery system. This is robust to lossy comms. Essentially, each of our zips have their own line of sight radios and also dual cell modem. And whenever they get in proximity to each other, they're communicating with each other. All right, that was a quick primer into our mission and current scale. Now I want to give you a bit of backstory as to why we developed our detect and avoid system. As I mentioned, our detect and avoid system is ready for production today. And you're the first folks outside of Zipline and the FAA to hear about it. So let's start with the question, how actually we integrate into the current airspaces we operate in scale today, without onboard detect and avoid? There are 3 key things that add up to achieve the necessary level of safety. First, due to regulatory constraints, our zip primarily operates at less than 400 feet AGL. Here's an example of a route that we fly along in Ghana, in Rwanda actually, to one of our furthest facilities. Due to the limitation of altitude, we typically have to climb and hug mountains and cross valleys. This inherently helps us separate zips from other air traffic. Second, we provide real-time visualization of our flight routes and vehicles to air traffic control in Rwanda and Ghana. This enables them to perform the necessary deconfliction with other aircraft and enforce flight route restrictions on our zips. You're looking at a screenshot of one of the tools that air traffic control in Rwanda and Ghana uses on a daily basis. And then lastly, the traffic densities in Rwandan and Ghanaian airspace are very low, as you can see in a Monday morning 10 a.m. flight radar snapshot. So flying at low altitudes aside, unfortunately, the benefits gained from air traffic control oversight and low airspace density is not a reality for drone operations in most of the world. For example, the US airspace. This diagram shows the US airspace breakdown. Areas that are controlled by air traffic control are Class B, C, E, and A. Class G airspace is where drones are typically primarily expected to operate, and they are uncontrolled and unmonitored. This actually represents more than 90% of the low altitude airspace in the US. I'd shown a typical Monday morning in ICRA. This is a typical Monday morning in North Carolina, Charlotte. There are orders of magnitude more traffic that we have to heavily account for. In addition, the prevalence of low altitude operations is high in these areas, as there's no real restrictions preventing flight below 500 feet, especially for helicopters and crop dusters. The airborne risk associated with the prevalence of low altitude traffic and the high traffic densities is amplified by one more factor. Many of these aircraft do not carry radio positioning equipment, also known as transponders. Here's a typical cockpit of a Piper Cub that has just analog dials. There's no radio equipment on board. A survey performed in 2019 by the FAA showed that transponder usage hovered at around 70% in certain regions and was especially poor in the Midwest and Alaska, where Alaska is about 33% actually. It's quite mind-boggling actually, the number of low-flying aircraft with no positioning equipment. How do these planes actually not hit each other? They just look out the cockpit. The pilot's ability to see and avoid is the approach used to solve the uncooperative detect and avoid problem. Which is aircraft with no positioning equipment. The effectiveness of this ability has actually been studied deeply, and it's not great, especially when you think about pilot reaction times. In some airspaces, such as close to airports, there's a radar, obviously, that has the ability to track these aircraft, and there's specific rules around operating in these airspaces. But they're sparsely distributed, and the moment you get below 400 feet, it's very, very hard to detect with radar. So it looks like we had to solve this. And to actually solve this problem at a truly national scale, our zips would have to have an onboard sensor. It's entirely impractical to try to think of a population of a whole country with populating the whole country with ground-based radars. We actually thought of that, and we were trying to figure out how we would achieve that. So this is where actually our journey starts, and I'm excited to walk you through this. Just checking audio. Everyone can hear me still? It's good? Awesome. Over there? All right, cool. The journey to start our onboard detect and avoid system. So first off, where did we start? We were thinking of what was the most obvious sensor to use. Like the biggest one is, let's try to have an onboard radar. Regulators are familiar with it. It's tried and true. So we started doing a bunch of testing with the current state-of-the-art radar systems that was pitched for sense and avoid. Right off the bat, for the field of view and elevation provided by that sensor, it took quite a bit of mass and was power hungry. To put 60 watts into perspective, our zips cruise at 600 watts. This radar sensor would consume 10% of our power budget, which was pretty wild. Nevertheless, we kept testing to better understand the system. A failure mode we started to find is that it turns out that aircraft that you're trying to detect that is between the drone and the ground and in the radar's field of view, the radar actually really struggles with the signal-to-noise ratio problem and does not detect. If you're familiar with this in the autonomous driving space, you're familiar with this problem as well. So in addition, just looking forward with a limited field of view was clearly not going to work. There's aircraft coming from everywhere. Here's a visualization of this in action. This is a visualization in a zip-centric frame, but shows characteristic general aviation tracks built by MIT Lincoln Lab and trained on years of historical air traffic data. Our zip is not to scale, keep in mind. In general, if a Cessna collides with another aircraft, it's the Cessna's fault. But if the Cessna collides with our drone, it's our fault. The drones do not have the right of way. And so we have to avoid and yield to all aircraft. Obviously, our zip needs to see 360 degrees. And so we started thinking about what other options did we have. We next looked at cameras with a critical need to ensure that we had a 360-degree coverage. It was evident that a bunch of cameras could actually achieve that 360-degree. We needed a bunch of cameras to achieve that 360-degree coverage. In addition, each of them would have to be at least 8 megapixels in resolution to ensure that we even had enough pixels on target. Cameras also actually inherently suffer from a geometric pain point. If an intruder is in a collision course with you, it's a dot that doesn't move, and it's really tiny, essentially. And finally, they're heavy and quite power hungry. The biggest kicker is that we fly regularly into and out of clouds and close to clouds. Medical emergencies do not wait for clouds to clear. And this is one of the Achilles heels of cameras. Basically, we need 360 degrees and also the ability in clouds. The next thing we started exploring was further up the electromagnetic spectrum, thermal images. In general, its performance was observed to be actually pretty great, especially with the background of the sky when you're detecting aircraft. However, the moment there's an aircraft below the horizon, this became problematic. There's actually 2 aircraft in this image, actually. And generally, it became a non-starter, as 1 to 2 megapixel imagers were the state of the art, which doesn't give us nearly enough pixels on target. You might be asking, why not LiDAR? This essentially became a non-starter, primarily due to detection range and the sparseness of points at long range. So we seriously tried everything we could on the electromagnetic spectrum, and we were stumped. How else could we actually solve this problem? So what about acoustics? There's a lot of historical literature where acoustics was the primary mode of detection of aircraft in World War I and early World War II, prior to the advent of radar. Here's a photo of soldiers listening for aircraft. Acoustic locators were used in mid-World War I to early World War II. These were passive devices that actually picked up noise of engines and propellers of aircraft. The horns you see give increased gain and directionality. In addition, the spacing between the horns provided the listener, who were the soldiers, the ability to localize the sound source. It was wild, but these acoustic locators could actually hear planes well over the horizon, tens of miles away. This is cool and all, but not really all aircraft are loud, as you may surmise. So even if we could solve this technical challenge, could we achieve the necessary level of safety that we wanted with an acoustic system? So we started digging into the data of all the aircraft that typically operate in the airspace and broke it down into various critical categories as shown. After digging into the data, we realized that 98.5% of these aircraft are propeller-driven, rotorcraft, or turbojet. This is great. So we would not even need to get 98% detections to achieve our level of safety. And as a side note, 98% is better than a pilot looking out the window, essentially. At this point, we weren't convinced about this idea, but it was super attractive because in theory, we could get 360 degrees field of view and in technology that's light enough to actually fly on a drone. So we asked ourselves, how can we actually kick the tires on this problem? Our first experiment was just putting some microphones on the ground to see how far we could hear the aircraft. It was actually really far. We could get at least easily detections up to 2 kilometers away on any day. The ground rig was also equipped. This ground rig was equipped with 6 microphones in a T-bar and a little 2-megapixel camera. So as an aside, given that we're going to be going deeper into acoustics, I know you're familiar with spectrograms, but here's a quick refresher. Essentially, any sound source generated is composed of sound waves at multiple frequencies propagating through the air. A microphone like ours on the ground recorder records the amplitude of sound at about 20 kilohertz in the time domain. The recorded sound is then converted into a frequency domain at specific time intervals using a fast Fourier transform, where dominant frequencies clearly show up at higher power levels. These frequency snapshots are actually strung together over time to form a spectrogram, where the color of the spectrogram displays the power levels of that frequency content. I mentioned easily being able to capture acoustic signals at least 2 kilometers away. I want to visually show what it looks like. Given that we had a camera on board that ground rig, here's a couple of examples of aircraft images captured with that rig and comparative spectrograms. We captured an SR-22, which is a general aviation aircraft, at about 3,000 feet, and it's that little dot on the camera in the red circle. At the same distance, the spectrogram shows distinctly a specific signature related to the blade pass frequency of the propellers of the aircraft and its harmonics. In a first principles basis, the typical RPM of an SR-22, it flies at about 2,000 to 2,500 RPM. It has 2 to 3 blades, and that translates awesome. Talking about acoustics. All right, I don't have to shout, and I think the acoustics here are pretty good, so let's go. Cool. So this translates to about 100 to 150 hertz for the fundamental frequency, and multiples of that in the harmonics. That's exactly what you're seeing in this plot. Similarly, we actually captured a commercial turbojet airliner at 10,000 feet. The acoustic signatures here are also unique and very different from that of an SR-22. The regions of high power are actually more broadband than the peakiness in the SR-22. Interestingly, we also captured air traffic when there were low cloud layers at our test facility. Here's an actual video of a Cessna 182 overhead going into and out of clouds. It's actually really hard to see, but it's actually a video. The same thing was evident. The acoustic signatures are clearly visible during this whole time. The same thing was evident from a Cessna 172 as well. It was actually a revelation, to be honest, on our end, to see how clearly these signals were, despite how degraded the camera performance was in dealing with it. So after our first set of experiments, we were like, let's start flying. We got excited and decided to make a jump into the air. We went straight for gold and started embedding our mics in a wing for an RC plane that we had to make sure it was the lowest drag and most ideal configuration we would like. So immediately we ran into a problem. In essence, there are 2 big problems once you get in the air. The image of a dog sticking its head out the window is actually to visualize what a microphone actually hears when it's in the air. The loud swishing sound that you imagine hearing when you stick your head out the window is primarily due to aeroacoustic noise generated around your head and the car itself. General aircraft aeroacoustic noise was our first problem. The second problem that we had to deal with was our own aircraft's propeller ownership noise. So these were the 2 big issues that we had to work on. A really good visualization of these 2 effects can be observed in the spectrogram shown. This is of sound recorded from our embedded mics in flight. The left side of the spectrogram is before we launched the plane, where low power levels are in dark colors, and in flight is on the right side, which have high power levels in bright yellow. The moment the aircraft was in flight, the first thing that you notice is actually the prevalence at around 300 to 400 hertz of our propeller ownership noise. The second key factor observed is actually this general aircraft aeroacoustic noise that critically impacts our low frequency regions, which is exactly where the region that we need to detect general aviation aircraft and helicopters. So we had a problem, and we figured out what we needed to do, and essentially what we did was we formed what we call a tiger team. It's essentially the smartest minds in Zipline that included mechanical engineers, applied mathematicians, systems engineers, to ruthlessly prioritize and focus on failing fast and achieving in-flight acoustic detections of a Cessna 172 up to 1.5 kilometers away, or know why it could not be done. With that in mind, we started with problem one, which was dealing with aircraft aeroacoustic noise. So we did not have to learn everything the hard way. We actually found the world's best aeroacoustic experts and consulted with them. So we could test without flying. We built our own anechoic wind tunnel, whose efficacy is actually pretty suspect for my taste. And then we started deeply iterating on microphone tip designs, really dialing in on critical locations that might allow us to handle this noise well. This included trying to put them above the wing, out in front of the leading edge, and we even tried to stick it on a giant spear, right, to get away from all the aeroacoustic noise. And it turned out this worked. And we started to get signal on its effectiveness. But obviously, a 4-foot spear in front of a drone is not that practical, to say the least. And not to mention, it's pretty scary looking and dangerous and so on and on. So how could we solve this problem without a 4-foot spear? Essentially, we ramped up our iterative development based on this anchor point of performance, and ended up trying over like 30 plus different hardware mounting iterations. This included modifying the trailing edge of the wing with an embedded mic. It involved adding trailing edge chevrons as seen on the 787 engine nacelle to help reduce the trailing edge noise, which was by far the dominant aeroacoustic noise generated by the aircraft. We explored various modifications that added winglets to the wing with integrated mic tips, and also a variety of wing-mounted configurations with adjustable mic tip designs. We finally cracked a tip design that worked and a placement that worked great, was practical, was low drag, low mass, and used very similar mounting approaches to our other wing-mounted pitot probes. We settled on 8 probes in an array of varying axial and lateral distances. I'll dive in why we needed an array in a minute. So here's a spectrogram from this vehicle in flight with a Cessna 172 track. Between the ground and in flight, the Cessna 172 was clearly detected and up to 1.5 kilometers away. It was one of those moments that made us take a beat and actually grab a beer and celebrate that occasion. So one big fail-fast problem had been solved. On to the next one. How do we actually deal with our Zips propeller ownership noise? To give a flavor of what we were trying to do, I want you to look at the frequency content of a typical signal of a Zip in flight. This was with a Cessna 210 in flight. First, we know the critical signal we are looking for here is the blade pass frequency, which is that line that's coming across of that Cessna 210. We also see a harmonic of that blade pass frequency right above it. In addition, there are some other noise sources. So there's our own propeller ownership noise, together with harmonic that's traveling through our Zip structure and actually over the air. And finally, there's also this aeroacoustic noise that's primarily due to wind gusts. We notice this bands of aeroacoustic noise, especially in windy and turbulent conditions. So how do we get rid of all of this unwanted noise and recover a higher signal-to-noise ratio of the exact thing that we need, which is the Cessna 210 really far away? So the technique leveraged here is called beamforming. In essence, beamforming works similar to our ears in discerning the location of a sound source. Imagine a sound source that's coming from the left as shown. From the speed of sound, we know that the sound source will reach our left ear first, and then followed by our right. Of course, there's other factors that underlie how our head deals with sound. But in essence, the difference in time and the speed of sound allows us to assess the direction of that sound source. That's the essence of beamforming. Now, with our wing with 8 microphones, frequency domain audio data from every channel is processed with an algorithm that estimates the azimuth angle to a far-field sound source, using phase shifts that can be observed between the individual microphones. What you're seeing on the right is a sample azimuth angle frequency beamforming plot for a single time slice. The signal from the intruder coming from -45 degrees, as shown on the left, shows up also at the same frequencies, and the same angle shows up at multiple frequencies corresponding to the fundamental frequency of the intruder and harmonics of it. Some ambiguous detections also arise with slightly lower power that must be dealt with, that we need to deal with. This is primarily due to the nature of the geometry of that microphone array. For the case of an intruder on 45 degrees forward on the left, there's an ambiguity actually 45 degrees aft and to the left, essentially. So the beamform spectrogram reduces the previous plot and takes the maximum azimuth signal for each frequency and gives us one column in the beamform spectrogram. This is then stacked together over time, essentially, to get a far-field noise source. This process helps us minimize the noise from nearby sources, given that the system explicitly looks for that far-field source and removes uncorrelated noise such as wind gusts. Most significantly, it actually also improves the signal-to-noise ratio of that far-field noise source. Essentially, compared to the previous spectrograms, this is a lot more magnified, and we could hear from a lot more further away. So we did it. We decided to go party at that point. But now, all of a sudden, this went from a crazy idea that we were trying to fail quickly to looking like a brilliant counterintuitive solution to a really hard problem. But of course, we were miles away from a solution that we could operate in production. This was 1 year into our journey, and that was actually 2 years ago, to be honest. I want to take you through the next 2 years of how we went from here to a production-level solution today. Something that works so well and so reliably that we can look regulators in the eye and tell them it's ready for integration into the airspace. To start this part of the journey, we had to build both hardware and software we could trust. Looking at the vehicle hardware itself, the vehicle configuration that we ended up with was an updated wing with an 8-microphone array along the wing. This was in addition to a transponder receiver located in the body for the proportion of aircraft that did radio transmit its position. The combination of those 8 microphones and our compute necessary to run the detection and tracking algorithms came up to be only 380 grams, and it ran about 6 watts. Looking a little more under the hood, the microphone probes mounted along the wing consist of specifically designed mic tips that house the microphone together with the mounting structure and necessary electronics to connect the microphone to the rest of the wing. Signals from all 8 mics are captured and time-aligned and sent to a perception compute that was housed in the center wing structure of the wing. Here, the perception compute is a low-powered GPU mounted on a PCBA, and also we have a heat sink to dissipate the heat generated by the GPU in flight. We take reliability and testing very seriously at Zipline. This has allowed us to reach the unsurpassed reliability and uptime levels that have enabled us to scale our operations where we are today. An example of one of these hardware reliability tests is what we call a flight load cycler. The flight load cycler is a device that essentially holds the whole aircraft with a wiffle tree-like mounting structure for the wing within a container. The flight load cycler subjects the whole aircraft to typical loads the aircraft would face in operations. Included within the container are also rain and heat simulators to ensure that the vehicle and its components are subjected to similar environmental conditions. This is conducted over multiple days whenever we have new hardware. In addition, we subjected our microphone to drop testing. This involved dropping the vehicle similar to what it would when it was landing from an emergency parachute deployment. This would allow us to understand key breakage points of the probe and perform necessary redesigns to handle these situations well. We also needed to subject our zips to launch and recovery loads, as those parts of the mission profile where the aircraft is subjected to the highest G loads. What you're seeing is our zips and probes subjected to launcher load cycling. ESD in the past has proven to be extremely problematic for our systems, which is electrostatic discharge. In flight, we're regularly hit by lightning. This has led us to develop hardware that is resistant to lightning strikes and ESD discharge in flight. What you're seeing is one of our EE engineers discharging a high voltage charge on one of our microphone probes. And whenever we integrate new hardware into a vehicle, a critical check is the impact of electromagnetic interference. This is to ensure that our GPS units, which is our primary mode of positioning estimation, is not affected by these components. Given that both our high volume operational environments are closer to tropical environments and our test facilities have been in temperate areas, we needed places where we could gather in much colder conditions. And so we have a high volume test facility in North Dakota to test our systems in cold, snow, and icing conditions to really stress test the boundaries and failure modes of the system. Finally, with more and more tested and reliable hardware, we initiated an extensive flight testing campaign to push our system to the limits, and we hired piloted intruders for ramping up our data collection efforts. I'll be talking more about this shortly. Next, I wanted to jump back into the software side of the picture. If you remember, we are able to leverage beamforming to extract the highest signal-to-noise ratio signal, and now we need to do something about it. For us, detection means two things. The first is whether there is an acoustic signature of a crewed aircraft, and second is what is the azimuth angle from which that sound source is coming from, which we call detection of arrival. From our dive into beamforming earlier, we know that each beamform map that you see is a slice of both frequency and azimuth content. And we use that as an input into our models. So we started very early on with a simple heuristic peak finding method. From there, we moved into looking at multiple time slices using various hand-engineered approaches, such as a random forest classifier model. And then as we started to gain and collect more data, it became obvious that an approach where we learned the key features would outperform previous methods. The visualization I'll be showing is with a hired intruder heading towards a zip from approximately 1.2 kilometers away and crossing by overhead the zip. The bottom plot shows the ground truth distance of the intruder relative to the zip and corresponds to the same outputs shown in the figures I'll be showing. The visualization on the left is a GIF of a rotated version of a frequency azimuth plot where high SNR shows up as yellow and low SNR in black. And the true intruder azimuth is in red. On the right is the output of our detection of arrival model that splits azimuth into 16 bins, of which the model signals high confidence in yellow and low confidence in dark blue. And basically you see that flip in signs because the aircraft is going overhead from the output. Nice, so we are getting detections. Can we improve our understanding of the intruder's locations now? We can use a tracker for this. We take each of these detections at each time step and incorporate them into a dynamic occupancy grid that's modeling and tracking the free space around the zip in a zip-centered NED frame. This method allows us to track the position of a potential intruder, and as our confidence increases here, the uncertainty of the position of the intruder is reduced. By choosing to model free space instead of a per-object tracking, this has limited the compute required for our embedded compute platform. An example output visualization of the tracker is shown here. We use a particle filter formulation in the dynamic occupancy grid. The ground truth of the intruder is shown in red. In blue, you see the particles tracking in the space over time. Higher density particles shows higher confidence. of occupancy. Now that we have a full end-to-end system, how could we make it better? We needed a lot more data. We tested over 30 different types of aircraft, where we put ground truth trackers on each of these aircraft for hundreds of hours. We had intruders fly in different representative patterns with variations of altitude, speeds to thoroughly cover what our aircraft would face in the real world. We wanted different geometries over varying terrains because intruders sound different from different angles, and different terrain reflects sounds differently. We went to North Dakota in the snow and Africa in the heat because sound travels differently in different atmospheric conditions. We tested with different aircraft in good and bad weather, varying wind conditions, and on and on and on. We also tested against false positive noise sources, such as lawnmowers and motorcycles. So how do we actually know how good this is, how good we are? To truly assess the performance of our detect and avoid system, we have to simulate our full system at a massive scale. There are 3 key pieces to achieving this. First, we have to have a software-in-the-loop simulation environment that accurately mimics the dynamics of the zip and has been validated by flight test data. Zipline leverages this simulation tool extensively internally and runs actual flight code to ensure that what was tested in simulation matches performance in flight. Next, we had to simulate the actual intruder traffic that we might encounter. This is achieved by leveraging encounter models that were developed by the great folks at MIT Lincoln Labs in collaboration with the FAA. And this is based on multiple years of historical data of tracks around the country. Shown here is a Monte Carlo simulation of 10,000 encounters from the historical tracks overlaid over a zip simulated flight route shown in black. The blue haze represents those tracks, and the red tracks are encounters that were of concern. By simulating these encounters, we're able to assess the risk of incursion or collision with and without a detect and avoid system and quantify its actual efficacy. Lastly, we had to add acoustics into the simulation of a DA system. One method was to do a physics simulation of acoustics in a realistic 3D world. But after consulting with experts, it was not going to be representative enough given the multitude of things that we have to account for. So we went with option 2, which was to build a parametrized model from our large-scale flight test data. The parametrized model correlates inputs available in simulation to outputs of our detection model. So in sim, we have a proxy detection model that statistically matches the same performance of our systems in real life, without having to simulate acoustics. Essentially, everything from the microphone input to the output of our tracker was parametrized. Now that we had a simulation environment that enabled us to statistically understand how our combined detect and avoid system would perform against intruders, we needed to work on improving the behavior side of the problem. This needs its own presentation, but I'll give you a flavor of what that is. In response to an intruder, our vehicle incorporates the acoustic track state information into a cost function. And then the system dynamically replans avoidance maneuvers to maximize for lateral and vertical separation. All of this is done while accounting for everything from winds, dynamic limits of the zip, terrain, obstacles, air traffic, and other zips. So where did this journey take us? We started by testing and ruling out obvious options: airborne radar, cameras, and LiDAR. Then we found a crazy option: acoustics, and spent a year trying to fail fast, but the more we worked on it, the better it looked. We then spent the next 2 years getting it ready for production, developing the production hardware, machine learning systems for detection, tracking systems, extensive data collection efforts, validation simulation, and finally avoidance behaviors. And now we have a great solution with 360-degree spherical coverage, long-range detections, and we're ready for operations. I want to step back and also call out and recognize the dedicated efforts of many of my brilliant and smarter colleagues at Zipline that have got us here today. So let's look forward. Earlier, I had mentioned a busy day last week being 855 flights a day, and equivalent to flying 2.6 times around the equator. We are only able to do this by standing on the shoulders of decades of progress by the robotics community over here. So truly, thank you for all your passion and hard work. But this scale represents Zipline just getting started on our mission, which is to make instant healthcare delivery a reality for all. So we are hyper-focused on our next milestone to achieve our mission. This milestone is 5 years out and is focused on what it would take to achieve 500,000 deliveries per day. This is equivalent to one rotation around the equator in a minute. The detect and avoid system I presented here is only the first of many perception-based autonomy capabilities we are working on to enable us to truly reach that scale. I look forward to sharing the journey of developing those technologies with you in the future. It was my pleasure to share this with you, and thank you for your time.
Thank you, Gavin. So we have time for 3 4 questions. So yeah, if you can align the microphones, we can start. Please.
Hi, Gavin. It was fascinating. Thank you so much.
For sure.
Yeah, I have a question. It's cool to use acoustics, but have you thought about, given your airplanes are already equipped with GPS receivers, have you thought about leveraging the existing ADS-B data and then to do the sense and avoid?
Absolutely. So we have ADS-B on board as well, but that represents about 70 to 80% of the proportion of traffic outside of near airport airspace. And so we have to still have that coverage of the last 20%. So ADS-B, we have to have that on board.
Got it.
Yeah.
And then if I can ask another question is, given your zips are flying kind of low in altitude and then most of the air traffic are flying high, I see that your microphones are more flat, like pointing forward. Have you thought about having microphones fly pointing more upwards?
So you mean like vertically distributed, right?
Yeah.
Absolutely.
Or maybe both, some of ones are pointing up and some microphones are
A
pointing
lot of our engineers would have absolutely loved it. Sometimes we're constrained by what the vehicle can give us, but there's work expanding that. And a few of our microphones actually do that. And another thing that I didn't talk about is that our aircraft rotates or can move in space. So at every time instance, we could actually rotate our aircraft and get that vertical resolution that we needed. So that, which is tracked over time. So.
Okay, thank you so much.
Awesome.
Hello.
Hello.
So you said you used acoustic signatures, right?
Yes.
To identify aircraft. I was wondering, at those speeds, does the Doppler effect affect anything? Like if I'm headed towards something, the frequency spectrum might be different than if I'm headed away from something.
That's a really good question. Yes, it does, but it's a bit too close, but we still leverage it. So it actually changes right as it crosses over us.
Okay, so the effect is really only when we're really close. If it's
Exactly.
farther away, it's not so
Not as much.
Great, okay.
Yep.
Thank you.
Yeah, thanks again for the amazing presentation.
Thank you.
Yeah, I was wondering a bit about the obvious question. What would happen at the moment if there's, for example, a glider plane in the way that doesn't have an engine?
That's a great question. That's one of the reasons why we broke down the problem in terms of what was the most riskiest part of the problem. 98.5% of traffic is actually gliders or hot air balloons and other stuff. And so right now, the way you deal with that is strategically mitigating it. And if a glider is at 400 feet, and I used to fly gliders too, if a glider is at 400 feet and not close to a landing port, they are having other problems than us. That's all I would say.
Okay, maybe I can ask one follow-up question. I don't know if this is the goal, but do you think with this avoidance system you can reach type certification or any kind of certification?
So we're going through that at the moment with the FAA, and we're trying to type certify this detect and avoid system.
Okay,
Yeah.
thank you.
Before everyone leaves, a few of my colleagues are actually below, and if you want to talk to us also a little, and we actually have a bunch of little Zipline models if anyone wants some, so you can come and get them. Go ahead.
Just one quick question. So what's the accuracy of your detection system, and what's enough for flying safely? And do your robots have barometer sensors? Because you mentioned
Barometer.
atmospheric.
Yes, we do have barometer sensors. In terms of detection accuracy, it depends on how well your tracking systems are, and it varies depending on distance. Actually, the closer it is, the more really good the tracking. And we do both. We track and output azimuth rates, and elevation as well on top of that.
Are you talking about tens of meters or?
No, it's actually angles. So in like.
You are just detecting the
We only care about angles and angular rates, and we can back that out easily.
Okay.
If you think about that. Yeah. And so it's about plus minus 5 to 10 degrees, I would say. Yep.
Thank you.
Okay, last question.
Yeah, how does rain and bad weather affect the acoustic signatures that you're picking up?
That's a good question. We are going through that testing right now. The good news is that, as I talked about incoherent noise being removed, raindrops actually get removed from beamforming, which is good. The moment you're in really heavy rain though, then we are trying to figure out what would be the next step to remove that out. But usually once you get in very heavy rain and really dense inclement weather, the aircraft that we actually care about detecting drop off massively. So that's that trade-off that we're talking about.
Thank you.
Yep.
Okay, let's thanks again, Gavin.